Welcome to Math with Professor V. This is part 2 of the video on solving the exam covering everything related to sequences and series for Calculus 2. This is an exam I gave back in fall of 2019. It's a long one, so here we are with part 2. Question number 12 says, express the magnitude of the error involved in using the sum of the first 4 terms to approximate the sum of the entire series. And here, notice we have an alternating series. We have the sum n equals 1 to infinity of negative 1 to the n plus 1. That makes it alternating times 0.8 to the n over n. So in order to answer this question, you need to apply the alternating series estimation theorem. And it states the following. So if you have some alternating series here, which is expressed as the sum negative 1 to the n minus 1 bn, and you know, you guys, it doesn't have to be n minus 1. It could be n plus 1, whatever, so long as it's alternating. And notice this is different. They said this alternating series equals s. It equals some finite number s. So that means it converges. Therefore, it has to satisfy the two conditions of the AST, which are listed here. Bn plus 1 is less than or equal to Bn. We know that that means Bn is decreasing. That's one way to show it using the definition. And then condition 2 was also satisfied, that the limit as n goes to infinity of Bn is 0. Then here's the interesting part. This is the magnitude of the error. This is the remainder that comes when you sum up the first n terms. And we put absolute value because all we're interested in is magnitude. We don't care if it's an overestimate or an underestimate. We just care, hey, there's error. That's equal to the real sum s minus, this is your nth partial sum, right? So this is the difference between the true sum and then wherever you stopped. If you summed up the first 5 terms, the first 10 terms, whatever. So if you take that difference and then you look at its magnitude, remember all we care about is just how much we're off by. That's always less than or equal to b sub n plus 1. So remember, b sub n is the portion of the terms that we look at without the alternating part attached to it. So if you add up the first, say, 5 terms in your series, the error is always less than or equal to whatever the 6th term would be, the one that follows it. So notice here we have an upper bound on the magnitude of the error, okay? If you add up n many terms, we know the error is always less than or equal to whatever b sub n plus 1 would be. Okay, and then if that sounds a little weird to you, let me just show you a little visual aid to hopefully help. So this represents some alternating series. Say we have the sum n equals 1 to infinity, negative 1 to the n minus 1, b sub n, okay? Your first partial sum, s1, would just be the very first term. So it would be negative 1 to the 1 minus 1 times b sub 1. So that's just b sub 1. So there's my first partial sum. There's b sub 1. Boom. Okay. What's the error? Well, here's the true sum. Here's partial sum. This is the error. This much right here. Well, the alternating series theorem, estimation theorem, tells me this error is less than whatever b sub 2 is. And you can just see, here's b sub 2. And obviously that's longer, greater in magnitude than this error right here. Let me continue illustrating. S sub 2, right? Your partial sum for the first 2 terms is going to be b sub 1 plus, now I'm going to substitute in 2 for n, so negative 1 to the first times b sub 2. So it's b sub 1 minus b sub 2. There's s sub 2. Where is s sub 2? Right here. Okay, if I only add up the first 2 terms, what's my error? The error is all this right here, because here's the true sum. Here's the error from the first 2 terms. So this is my error. Alternating series estimation theorem tells me that error is less than or equal to, in magnitude, b sub 3. Oh yeah, for sure. Look at b sub 3 here. It's longer. It's greater. and so on and so forth. If you look at the error from just adding up the first 3 terms, say you stop at s sub 3, you only add up these 3. This is the error right here. That's less than or equal to the magnitude of the 4th term. We're just talking about magnitudes because we know they're bouncing back and forth, positive, negative, but that's what helps us have this estimation theorem, because each partial sum undoes a little bit of what was added before. Okay? So, on that note, the actual solution to the problem involves very little work because it wants us to estimate the magnitude of the error. So we're just going to give an upper bound on the error using the sum of the first 4 terms. So what that tells me is we're only adding up the first n equals 4 terms. So the magnitude of the error, or the remainder, right, from summing up just the first 4 terms, is less than or equal to b sub 4 plus 1, which is b sub 5. Okay, can you identify b sub n from the series? It's the portion without the negative 1 to the n plus 1 part. So b sub n is 0.8 to the n over n. And all I need to do is figure out what's b sub 5, and that's my answer. So 0.8 to the 5th divided by 5, and it comes out to about 0.065536. So depending on what your instructions are for rounding, you can leave it like that, or do 6.55 times 10 to the negative second. And that's it. So the question sounds a lot more intimidating than it really is. You just need to know the alternating series estimation theorem. All right? Good, let's move on. All right, next question asks us to find the interval of convergence of the series. Anytime you're asked to do this, do the ratio test. So here we go. Ratio test tells us we take the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So let's see what we got going on here. We have the limit, n goes to infinity, absolute value. Substituting in n plus 1, everywhere I see n, I have x minus 1 to the n plus 1 over, be so careful here, you guys, 3, put parentheses around this n plus 1, and then factorial, okay? And then dividing by a sub n is the same as multiplying by the reciprocal, so I'm just going to skip to that. So we'll have 3n factorial up top, and then x minus 1 to the n down here, all right? Good. Now I want you to pay attention to this part here because it's crucial that you distribute the 3 throughout, otherwise you won't get the right result. So this is going to simplify to 3n plus 3 factorial, yeah? Okay, so now we've got the limit, n approaches infinity, absolute value. Let me break up x minus 1 to the n plus 1 into x minus 1 to the n times x minus 1 to the first. And I'm doing that because I want to cancel with this x minus 1 to the n down there. Now look at these factorials. You always expand the larger one until you get a term that matches the smaller one on the other side of the fraction to cancel. So what do I mean by that? I'm going to rewrite this as 3n plus 3 times 3n plus 2 times 3n plus 1, and then finally we have 3n factorial, okay? So when you're expanding something like 3n plus 3 factorial, it keeps going down one integer at a time. 3, 2, 1, now you're down to 3n factorial. And I stop there, don't keep going, because I see, oh, there's 3n factorial on the other side that I can cancel with it. Yes? Oh, good. Okay, so then now you have a little cancel party. It's so satisfying. X minus 1 to the n is gone. 3n factorial is gone. Okay. And then I can take absolute value of x minus 1 out of the limit. Okay, and don't have a panic attack. This is the limit as n approaches infinity. So n is changing, but in this limit, x is a constant. And I like to do that just so we can focus on the limit and not have so much stuff running around, you know? So x minus 1, keep the absolute value though, right? Outside, and then I'm going to have limit, n goes to infinity, 1 over, and now I don't need absolute value because n's always positive. I really needed it just for the x, right? And then we'll have 3n plus 3, 3n plus 2, 3n plus 1. How are we doing? Okay, good. This limit's not bad because n's going to infinity. The denominator's going to infinity. I have a constant in the top. So this whole thing's going to 0. Very good. So then I'm just left with absolute value of x minus 1 times 0, which is 0. And remember, what test did we just use? We used the ratio test. And what I require is that this limit comes out to be something less than 1. Well, it's 0, independent of what x is, and that's always less than 1. So what does that tell me? Well, that tells me this series will converge regardless of what I plug in for x because the result from the ratio test is 0, which is less than 1. So I can say that the radius of convergence is infinite. Radius of convergence is infinite. And if they want the interval of convergence, it goes from negative infinity to infinity. You could even add in this limit here is less than 1 for all x's. That means for all or for every x. That's a real number. Ooh, look at us. Okay, good. That's it. So not too much work on that one. Let's move on to another example, same directions. So we're asked to find, again, the interval of convergence for this series. So start off the same way. We're going to do the ratio test. Okay, so we've got the limit as n approaches infinity. You know, on a rare case, you can do the root test, but I would say like every single time the ratio test will work where the root doesn't. So I would go for ratio. I'm trying to think if there's any exceptions. Nothing is coming to mind. All right, so we have x minus 2 to the n plus 1 over 3 plus 3 times n plus 1. And then dividing by a sub n, I'm going to put 3 plus 3n here. And then x minus 2 to the n. Okay. Again, I'm going to break this up into x minus 2 to the n and x minus 2 to the first so I can cancel it with this guy. Make sure you're still writing lim and keeping your absolute value, okay? So this is x minus 2 to the n, x minus 2 to the first over, what's this? 3n plus 3 plus another 3. So that's 3n plus 6. And then we've got 3 plus 3n, x minus 2 to the n. All right, so here we go. Cancel party time. X minus 2 to the n is gone. And then that's all the canceling fun we can do. Don't you dare think about canceling those 3 n's or something horribly illegal like that. This, unless it's completely factored, no canceling. Like this stays together. This is a little family. This is a little family. You could take a 3 out and then it's n plus 2 and a 3 out and it's n plus 1. That's as wild as you can get, okay? I don't even want you thinking about anything else. Okay, so we can cancel those 3's if you're so inclined. Now, I'm going to take this x minus 2 absolute value outside of the limit so I can focus on everything else. So absolute value x minus 2. Then we have limit n approaches infinity. I'm going to have now n plus 1 over n plus 2, right? Everything else canceled out. Okay, now as we take this limit, n's going to infinity, numerator's going to infinity, denominator's going to infinity. No, you cannot do L'Hopital's rule because n represents the term number in the sequence, right? So that's not differentiable. It's not a differentiable function. So you could do your precalc shortcut, right? Since the degree is equal for the numerator and denominator, you just look at the ratio of the leading coefficients. But if your calc teacher's picky, then your other option is just divide by highest power of n in the denominator, which is the same as if we multiplied by 1 over n. And then we have absolute value x minus 2 times the limit. N approaches infinity. This will be 1 plus 1 over n. Down here we'll have 1 plus 2 over n. And then now you can just take the limit. 1 over n and 2 over n go to 0. And then we're left with 1 over 1. So we still have absolute value x minus 2 times 1. And then just remind yourself, okay, I applied the ratio test. So in order for this series to converge, this limit has to be strictly less than 1. Okay, that means absolute value of x minus 2 has to be less than 1, which if I rewrite it without the absolute value bars, that means x minus 2 is between negative 1 and 1, which is the same as saying, if I add 2 everywhere, that x is between 1 and 3. Okay, I know for all the values between 1 and 3, the series will converge, but I need to test what happens at the endpoints 1 and 3, and we test each of them separately. So our original series, if you'll remember, it was the sum, n equals 1 to infinity, x minus 2 to the n over 3 plus 3n. So let's test the endpoints. You have a preference? Let's do 1 first. It doesn't matter. Okay. So if I substitute in 1 for x, we're going to have the sum n equals 1 to infinity, 1 minus 2 to the n over 3 plus 3n. That ends up being negative 1 to the n over 3 plus 3n, right? And then now you just have to pick a test that applies. Well, as soon as I look at this guy, I go, hey, it's an alternating series, so let's use AST. What's b sub n? 1 over 3 plus 3n. Very good. So first thing I have to show is bn decreasing. And this is straightforward. We can just use the definition because bn plus 1 is 1 over 3 plus 3 times n plus 1. If I'm making the denominator bigger, of course that's smaller than what the term prior was, bn, so that's good. And then the next thing I want to check is the limit as n goes to infinity of bn 0. So the limit as n goes to infinity of 1 over 3 plus 3n, that clearly goes to 0. So both conditions are satisfied. So that tells me the sum, n equals 1 to infinity of negative 1 to the n over 3 plus 3n converges by AST, by the alternating series test, which tells me that the value x equals 1 is part of the interval of convergence. So I can go ahead and now make this inclusive. Okay, but let's summarize that. So this means x equals 1 is an element of, or it belongs to, the interval of convergence. I'll abbreviate. Okay. Cool. That's for x equals 1. We also have to test what happens for x equals 3. And don't assume because one converged, the other will, or if one diverges, the other will. You just have to test them separately, okay? So here we go. We've got the sum. N equals 1 to infinity. And it was x minus 2, so 3 minus 2 to the n over 3 plus 3n. Well, 3 minus 2, that's just 1 to the n, which is 1. So this is the sum, n equals 1 to infinity of just 1 over 3 plus 3n. Okay. So look at this series. It reminds me of the harmonic series because there's no n's in the numerator and I have n to the first in the denominator. So this is reminding me of the harmonic series, which is the sum n equals 1 to infinity of 1 over n. Okay, I know any multiple of the harmonic series will also diverge. So just because there's a 3, that doesn't change anything. I could multiply by 1/3 and it would also diverge. But there's this plus 3. Now we know long term that's not going to do anything to affect the convergence or divergence of the series. But Because it's plus 3, we can't use direct comparison to show that our series diverges also, because each of the terms of our series are a little bit smaller than the terms of the harmonic series. So remember, if you're doing direct comparison test, you have to show that the terms of your series are larger than the terms of some divergent series. And if you can't show the correct inequality, then you use limit comparison instead. So that's what I'm going to do now. We're going to use limit comparison test and just look at the limit as n approaches infinity of the terms of our series, 1 over 3 plus 3n, over the term of the harmonic series, 1 over n. So this is going to be the limit. N approaches infinity. Dividing by 1 over n means n gets multiplied in the numerator. And then we still have 3 plus 3n down here. Divide everybody by n. Divide everybody by n. And then we've got the limit. N approaches infinity of 1 over 3 over n plus 3. Good. So then as n goes to infinity, 3 over n goes to 0, and this limit comes out to 1/3. Well, what do I care about the limit being 1/3? We just did limit comparison test. So what are the conditions for limit comparison test? As long as this limit is finite and not 0, it tells me that my series behaves the same as the one that I compared it to. Well, what does the harmonic series do? It diverges. So that means my series and the harmonic series are twinsies. Ours diverges also. So this means that the sum, n equals 1 to infinity, 1 over 3n plus 3, diverges also. Okay, so the number doesn't tell you whether it converges or diverges. It just tells you that your series does the same thing as the one you compared it to. This could have been 47 million. I would have still had the same conclusion, okay? So what does that tell me then? That x equals 3 is not part of the interval of convergence. How do we write that with math symbols? X equals 3 does not belong to the interval of convergence. So for our final answer, the interval of convergence includes 1, but not 3. And everything in between is good to go. All right. That's a very involved and thorough problem. I would expect one like that on a test. If I was a student, because your teacher can check if you know ratio test, AST, limit comparison test, they can check that you know a lot of different tests in one problem. So it's a good one to put on there, okay? All right, moving on, question number 15. Find the Taylor polynomial of order 3 generated by f at a. So f of x is 1 over x plus 6, and a is equal to 1. So let's go ahead, let's make a table. And if it's order 3, then we're just stopping when n is 3. So we'll make a table for n, the nth derivative at x, and then the nth derivative at 1. Okay, and we're just going to go 0, 1, 2, 3. Remember, your formula when you get a Taylor polynomial is that f of x equals the sum, n equals 0 to infinity, nth derivative at a, x minus a to the n, over n factorial. Just memorize that. When they say order 3, that means we're not going to do infinitely many. We're going to stop at n equals 3. So we just do the first 3, okay? So the 0th derivative at x just means give me back the original function. So that's 1 over x plus 6, which is x plus 6 to the negative first. I'm going to think of it that way just so we can take derivatives more easily, okay, you guys? And then the first derivative would be negative x plus 6 to the negative second, or negative 1 over x plus 6 squared. Another derivative, you'd have positive 2 over x plus 6 cubed, and then negative 6 over x plus 6 to the fourth. Okay, and then I'm going to substitute in 1 for all my x's. So this will be 1/7, negative 1 over 49, positive 2 over 343, and negative 6 over 7 to the fourth. I don't give my students a calculator, so like they could leave it 7 to the fourth, but if you have one, 2,401. Okay? Good. So now let's go make our Taylor polynomial order 3. You could call it P sub 3 of x. I'm going to call it T sub 3 of x for Taylor polynomial. So just keep in mind, you always have 3 parts to each term in a Taylor series. Nth derivative at a, x minus a to the n factorial on the bottom. The first part we have from our table here, okay? Then you just add in the other 2 parts. But just remember, Taylor polynomial, there's 3 parts to each term. Let me show them to you again. 1, 2, 3. You got it? Good. So for the first term, which is n equals 0 term, we're going to have 1/7 x minus a, which is 1, to the 0 over 0 factorial. Let me color code. 1, 2, 3. How we doing? Good, right? We're golden. Plus, now I need n equals 1. So we have negative 1 over 49, x minus 1 to the first over 1 factorial. Again, nth derivative, first derivative at a, x minus 1 to the first this time, 1 factorial. Then keep it going 2 more times. Pause the video, try it on your own. See if you can do it. Plus 2 over 343. I hope you paused it. Because, you know, if you watch me, you're like, I got it, it makes sense. And then when you sit there and you have to do it by yourself on the test, you might have a meltdown. I didn't color code this right. Are you yelling at me? I hope so. Okay. Got it? 1 more. That's it. Just 1 more. Plus, let's scoot all of this. Scoot. Okay, last one. Negative 6 over 2401 x minus 1 cubed over 3 factorial. 1, 2, 3. Good. Okay, now we just clean up, and don't worry, it's not so bad. I'm not going to highlight anymore. This is 1/7. X minus 1 to the 0 is just 1. 0 factorial is 1. Okay. Minus 1 over 49 times x minus 1 to the first. Plus 2 over 343 times x minus 1 squared times 2 factorial is 2. So I have 1/2. See, these 2's are going to cancel. Minus 6 over 2401 times x minus 1 cubed times 1 over 3 factorial is 6. See how those cancel as well? These are gone. Okay. So then I would say the most simplified version, I really wouldn't sit there and like distribute. You want to see the x minus a part altogether most of the time. Check with your professor though, okay? 1/7 minus 1 over 49 x minus 1 plus, now it's just 1 over 343 x minus 1 squared minus 1 over 2401 x minus 1 cubed. And I would say leave it like that, okay? But like I said, always check with your instructor how they want the final answer. And do it. Do what they say. All right, very good. Moving on, find the Maclaurin series for the given function using known Maclaurin series. So not using the definition, not the long way, making a table, just using a known Maclaurin series. So the first thing I notice is, there's sine of something. So let's see, do you remember what the Maclaurin series is for sine of x? The way I think of it is sine is an odd function, so it's all odd terms. So n equals 0 to infinity, that's always there, and then it's alternating, -1 to the n. And then we express odd numbers as 2n plus 1 usually. So it's x to the 2n plus 1 over 2n plus 1 factorial. Just memorize it, okay? From here, I'm looking, okay, so instead of sine of x, we have sine of 6x. So I'm going to replace x with 6x. So sine of 6x as a Maclaurin series would be the sum, n equals 0 to infinity, -1 to the n, 6x to the 2n plus 1 over 2n plus 1 factorial. And then we're pretty much there. I just have to divide by x. And that's the same as just multiplying by 1 over x. So now my job is, let's clean this guy up. So there's just a couple things to do. So we have the sum, n equals 0 to infinity, -1 to the n. You do want to distribute that 2n plus 1. Okay, so you're going to have 6 to the 2n plus 1 times x to the 2n plus 1 over 2n plus 1 factorial. And then now I also have that little x down there, this guy. And then hopefully you see one more thing we can do, right? So x to the 2n plus 1, that's x to the 2n times x to the first, right? So that x can cancel with the x in the denominator. And at long last, we have Maclaurin series. So sine of 6x over x, let me just rewrite what they wanted, is the sum, n equals 0 to infinity, -1 to the n, 6 to the 2n plus 1, x to the 2n over 2n plus 1 factorial, okay? And if you're having a hard time memorizing your Maclaurin series, in the video lecture, I go over patterns and some useful tips to help you memorize the Maclaurin series for sine x, cosine x, e to the x, etc. So that video is linked in the description. I would go check it out if I were you, if you're struggling with that. All right, moving on. Okay, question 17, use series to evaluate the limit. We have the limit as x approaches 0, e to the 2x minus 1 minus 2x over x squared. And, you know, we could use L'Hopital's rule, but they told us specifically we have to use series to evaluate the limit. So that's what we're going to do. When they say use series, they mean replace whatever terms you can with some known Maclaurin series, simplify, and then find the limit. And I have a whole video just on this topic if you need more examples. So e to the 2x, that's the one part of the limit that I'm going to replace with an infinite series. And if you need a little refresher, e to the x is a Maclaurin series, is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. So e to the 2x is 1 plus, now replace x with 2x, plus 2x quantity squared over 2 factorial plus 2x quantity cubed over 3 factorial plus 2x, okay, we got it, right? All right, enough, plus ... So you're just going to come to the limit here, and instead of e to the 2x, you're just going to write out however many you need. I know, that part feels always awkward. You're like, do I do 3, 4... whatever you need to see a pattern and still have stuff left over. And usually these limits are like concocted in such a way that some terms are going to cancel. So you just want to have enough left over after the cancellation. Like I'm already looking 1 and 2x, those are going to cancel. So yeah, let me leave these 3. That'll make me feel good. So instead of e to the 2x, I'm going to write 1 plus 2x plus 2x squared over 2 factorial plus 2x cubed over 3 factorial plus 2x to the 4. That one you probably could have done without, but you know, the more the merrier. Okay, good. Minus 1 minus 2x over x squared. Good? All right, cool. This part's the e to the x part. So we can cancel now. Lovely. The 1 and the 2x are gone. 1 and 2x, you are gone. And then let me clean up a little bit more. So this is limit x goes to 0. I'm going to expand everything. So I'll write this as 4x squared over 2 factorials 2. 2x quantity cubed is going to be 8x cubed over 3 factorial is 6. Plus this would be 16x to the 4th, 4 factorial 24. Plus dot dot dot. Oh, I forgot that. Oh my God. That's wrong if you don't have it. Okay. And then all of this is divided by x squared, which is the same as multiplying by 1 over x squared. And then look what happens. So this is going to distribute. Boom. 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 This x squared will cancel. The rest of the terms, this will be x to the first. This will be x squared. Then x cubed, so on and so forth. So then we have the limit, x goes to 0, 4 divided by 2, that's 2, plus 8x over 6, plus 16x squared over 24, plus blah, blah, blah. What's important here is that all the rest of the terms, I don't need to write them out, will have x in the numerator. And this is the limit as x goes to 0. So everybody else from here on out is just going to go to 0 because they all have x's in the numerator. So these are all just a bunch of zeros. The only one that's not is the 2 out front here. So this limit is 2. And if you're nervous, if you did it right, you could still just go back to the original limit. It's indeterminate, right? Yeah. And then just do L'Hopital's rule to make sure that you did the rest of it right. Okay. Very good. Moving on. Find the sum of the series. Do you remember what I said in part 1? You can only find the sum of the series if it's geometric, telescoping, or a Maclaurin series. Well, this is not geometric. It doesn't look telescoping to me. I wonder if it's a Maclaurin series. Why, yes, it is. Notice, odd, 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 right? Odd powers, odd factorials, alternating. We just looked at this Maclaurin series. Remember, sine of x is the sum. N equals 0 to infinity, negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. So what is x here? Well, it's 2/3. The 2n plus 1 factorial is 1 factorial, 3 factorial, 5 factorial, 7 factorial. Negative 1 to the n is the alternating portion. The only part that's not accounted for is x to the 2n plus 1. So if you want to rewrite this sum, you could. You could write it as it's 2/3 to the first minus 2/3 cubed times 1 over 3 factorial plus 2/3 to the fifth times 1 over 5 factorial, etc. So once you recognize that pattern, then there's pretty much no work. The sum of the series is just sine of x. X is 2/3. And that's it. You're done. I know. All right. Hopefully that was fun. Next, use power series operations to find the Taylor series at x equals 0 for the given function. So when they say Taylor series at x equals 0, that's the same as a Maclaurin series. But what they want us to do in this case is use power series operations. So I'm not going to use like the definition for a Maclaurin series. Power series operations means we're going to take advantage of the fact that we can differentiate and integrate power series and all of that sort of stuff in order to come up with the Maclaurin series or power series representation for this function here, f of x. If you haven't watched my video, Power Series Made Easy, you need to because it's a game changer. So there's only 3 scenarios like I break down in the beginning of that video. And as soon as I see the denominator is raised to a power higher than 1, I know I'm going to differentiate the OG power series. So remember, this one needs to be burned in the brain. 1 over 1 minus x. Power series representation for that function is the sum, n equals 0 to infinity, x to the n. That's like your home base. Now, since there's a 9x instead of plain old x, I can come up with a power series representation for that function. It would be the sum, n equals 0 to infinity, of 9x to the n, right? Which, yes, expand it or distribute that n through. So this is the sum, n equals 0 to infinity, 9 to the n, x to the n. Now, that's not the function that I want a power series representation for. Mine is squared. And I'm going to tell you something very important right now. As a Calculus 2 student, the answer to your questions or your issues is never to square an infinite series. You may need to do it later in your math career, but never think about squaring an infinite series. It will only make life worse. So you go, how do I take this denominator from the first and make it to the second power instead? You're going to differentiate. That's the answer. You're going to differentiate. So you're going to think of this instead as 1 minus 9x to the negative first, okay? So 1 minus 9x to the negative first equals the sum, n equals 0 to infinity, 9 to the n times x to the n. We differentiate with respect to x, both sides. Both sides. Okay. Left side derivative, don't forget your chain rule. So it's going to be negative 1 times 1 minus 9x to the negative second times derivative of the inside, which is negative 9. And then we have to differentiate the infinite series. Anytime you take the derivative of an infinite series like this, the index has to scoot up by 1 because the n equals 0 term is a constant. And when we take the derivative of a constant, it's 0. Very good. So now we're going to start at n equals 1 to infinity. Now, 9 to the n is just a constant, so don't touch it, don't do a thing to it. Derivative of x to the n is going to be n times x to the n minus 1, okay? Good, good. Now we just clean up and then we adjust if need be. So let's see, negative 1 times negative 9, this is going to be positive 9 over 1 minus 9x squared. And then this stuff, there isn't really anything to clean up. N equals 1 to infinity, 9 to the n times x to the n minus 1. Now what you do is you look at this derivative here, and you look at f of x, and you go, are they the same? Almost. I got the squared sorted out. There's a 9 here, and there needs to be a 1. That's totally fixable. We multiply by 1/9, 1/9. Okay. Fabulous. So now these are gone. I just have 1 over 1 minus 9x squared. This is the sum, n equals 1 to infinity. Now, if I have 9 to the n and I'm multiplying by 1 over 9, that's going to be 9 to the n minus 1 times n times x to the n minus 1. And then when it's possible, you want to try to write your final series with just x to the n, not n minus 1, and it'll clean things up nicely. So in order to do that, if I want this to be bigger by 1, I need to start 1 lower. They always move in opposite directions. So when you're shifting your indices, I need to go n equals 0 to infinity, and then I'll have 9 to the n times n plus 1 times x to the n. And there's f of x. Boom. How was that? If you have a really rough time with these problems, then like I said, watch that video, Power Series Made Easy. It'll change your life. And I'm not even being dramatic. Last question says, use substitution to find the Taylor series at x equals 0 of the given function. So one thing you could do is, if you know your Taylor series at x equals 0 is same as Maclaurin series. If you know the Maclaurin series for natural log 1 plus x, you could use it and cancel out some terms. I've shown that method before. I think it's more useful if we practice using power series operations. So I'm going to do it that way, even though the directions didn't say specifically to use that method. I think it works out better. So I'm going to call this all f of x. Natural log of 1 plus x cubed over 1 minus x cubed. And anytime you're trying to find a power series representation and you see there's natural log in it, you're going to differentiate your function, find a power series, and then go back and integrate. So before I differentiate this, let's use our log properties to expand and make life a little easier for ourselves. So this is natural log 1 plus x cubed minus natural log 1 minus x cubed, right? Okay, so let's take a derivative, f prime of x. Derivative of natural log 1 plus x cubed, it's going to be 1 over 1 plus x cubed. And then don't forget we have to do the chain rule. So we should have 3x squared in the numerator. Minus derivative of natural log 1 minus x cubed would be 1 over 1 minus x cubed times negative 3x squared. Exactly. So this is 3x squared over 1 plus x cubed plus 3x squared over 1 minus x cubed. Now you could start trying to get a power series representation for each of these terms separately, but then to combine your two power series into one is going to be some work that I'm not looking forward to. So instead I'm like, let me try to get a common denominator, and it works out really beautifully. So I'm going to multiply this one by 1 minus x cubed top and bottom, and then the next one by 1 plus x cubed. And then look what happens. So we'll have 3x squared minus 3x to the 5th plus 3x squared plus 3x to the 5th over, and then 1 minus x cubed times 1 plus x cubed is going to give me 1 minus x to the 6th, right? Because it's a difference of squares. All right, and then 3x to the 5th cancels out. So now I just have 6x squared over 1 minus x to the 6th. Oh, this is going to be easy peasy to find a power series for. So remember, 1 over 1 minus x is the sum, n equals 0 to infinity, x to the n. Start off just focusing on this x to the 6th. So 1 over 1 minus x to the 6th is going to be the sum, n equals 0 to infinity, x to the 6th to the n. And then what else do I need? Well, we have a 6x squared up top, so I'm just going to multiply by 6x squared up top. Multiply by 6x squared. Now clean this guy up. Call in the cleanup crew. So this is the sum, n equals 0 to infinity. This is going to be x to the 6n times 6x squared. We can add these exponents and then just keep the constant there. 6 times x to the 6n plus 2. Beautiful. Does that equal my original function? No. Who is this? Who are you? You are f prime of x. Okay, so I have a beautiful power series, but it's a power series for f prime of x. I need a power series for f of x. How do we get from f prime to f of x? Why, we take an antiderivative. Both sides. Both sides. Don't be freaked out, okay? It looks way worse than it is. If you want to like scare Calc 1 students, sure, show them this. But in all reality, ignore this guy, ignore the constant, and just think to yourself, when I take an antiderivative, I add 1 to the exponent on x and divide by the new exponent. Everything else just comes along for the ride. No panic attacks, just rewrite it. So you'll have x to the add 1, 6n plus 3, divide by the new exponent, oh my, 6n plus 3, and then just don't forget plus c. Okay, so this is f of x. Good? I told you it looked worse than it really was. The actual math in it is very straightforward. How do you find c? Well, this power series is centered at 0 because the base is just x. If it was like x minus 1, then it would be centered at 1. Pretty much never, doesn't happen that often. Anyways, this is f of x. I'm going to plug in 0 to find c. So f of 0 would be natural log of 1 plus 0 over 1 minus 0. That's natural log of 1, which is 0. F of 0 is 0. And I can see here, okay, f of 0 would be the sum of 6 times a bunch of zeros plus c So this whole sum is 0. So C is 0. Fabulous. I did a few in that other video that I keep talking about where C is not 0, in case you're curious. So we're pretty much there. I know that C is 0. F of x is the sum. N equals 0 to infinity. 6 times x to the 6n plus 3 over, I can factor a 3 out, and then that's 2n plus 1. And then I can cancel out the 3 and the 6, and now that's a 2. And you can leave it there, or you could put it outside the sum. Let's do that. So this is 2 times the sum, n equals 0 to infinity, x to the 6n plus 3 over 2n plus 1. And I know I told you, you always want to try to end with x to the n, but in this case, it's just not possible. If I shifted to n equals 1, this would just be 6n minus 3, which looks no better than what we have, so it's not worth doing. Just leave it alone. Okay, so that concludes the video. I didn't go super in-depth into explanation and the theory behind solving these the way I do in the lecture videos. I just didn't want this to be like an 8-hour video. So if you feel like any of the topics, you just needed a little bit more of a breakdown, I totally get it. That's why I've linked all of the video lectures for this unit in the description of this video. So if there's anything that's a little fuzzy and you just want more examples, more of a breakdown, slow explanation, then that's where you need to go. But hopefully this is like a good overview so you can see where you are and identify any weak points before you take your exam on sequences and series, okay? All right, thank you guys so much for your support. Don't forget to give the video a thumbs up, subscribe if you haven't already, and then follow me on Instagram, TikTok, Twitter, Math with Professor V. Bye, guys.